my favorite inference framework is vLLM, and we are using it on our infrastructure as well. And now we're going to hear more on how we can get more out of our GPUs. Welcome, Eldar and Max from Red Hat.
Thank you. Yeah, so my name is Eldar. I'm a researcher at Red Hat and the Institute of Science and Technology of Austria. And I basically work on efficient inference, specifically now for vLLM.
Yeah, and I'm Max. I'm a solution architect with Red Hat. Happy to be back and talk about quantization in vLLM. Eldar,
yeah,
let's get started.
Thanks a lot. So yeah, basically the idea for today is going to be like, this should be like some kind of like a tutorial style talk where everyone should get something new from this. Those who are not experienced with quantization and those who actually are a little bit like more advanced users of that. So just so we are all like starting from the same point, the quantization is a process of reducing the bit width, so the precision of the weights or the activations in like let's say a language model. What I mean by this is basically like in the original format, like the models that are being released are usually like their weights and activations are represented with 16 bits. So there's like a high granularity there. So this is like this Gaussian curve here. So the values can take any floating point value from this range. During the quantization process, what we're trying to do, we are trying to map them down into the lower granularity range into like a smaller, like a discrete buckets. During this process, what we have to do is that we have to actually change some of these values because, like in this example here, these two values will be mapped to the same bucket because they don't have their corresponding values in on this lower granularity space, which means that during this process we will be introducing some error, and the entire game with quantization is how do we actually minimize this error such that we do not destroy accuracy of our model once it's quantized. What this means in practice is usually the models that are being trained and released these days are in the brain float 16 format, which has this very, very wide range here. And what we're trying to do through the quantization, we are trying to find the proper scaling factors to map all of the values from this range into, for example, int8 range. So we are reducing the range to just these values from -127 to +127 by finding a proper scaling factors to map all of these values into this range. So why quantization matters in general? So basically, it reduces the memory footprint of your models. What this means in practice is that it's going to lower your deployment costs. So instead of requiring n GPUs, we can reduce this to n over 2, or like if you're doing like FP8 to FP16 to FP8 quantization. And the good part about that is that it's going to make our deployments even faster because now we require less GPUs, which means less communication between the GPUs during the inference time. So this inference efficiency that we're getting from quantization is basically enabled through two paths. The first path is via faster weight loading. So this means that when we are quantizing the weights, we are reducing the number of bits that we are using to represent the weights, which means that we have less data to move around inside our server, which is going to be one source of the speedup. The second source of the speedup will be by using lower precision computational tensor cores on our GPUs. And this is going to be like a much faster way to do matrix-matrix multiplication, as we will see later on. And the final piece here is that the real-world adoption of quantized models is steadily increasing. So this is basically like usage statistics from vLLM. All different colors, you shouldn't be able to read this. Like it just represents different quantization schemes which are supported in vLLM and other people are using. And this is basically ranging from February last year to February this year. So it's like steadily going up. Where does quantization fit inside an LLM? Basically here, so this is the standard like a llama model that we get like from like a Hugging Face transformers implementation. Basically, at the input side, we have some embeddings to map the tokens into some n-dimensional vectors. Then we have like n identical transformer layers, and then we have maybe some normalization layer and the LM head. The crucial piece that we are focused on are these like n transformer layers here. They're all identical, and they have more or less the same structure. We have some input layer norm, we have the self-attention part, again the layer norm, and the MLP part. The interesting thing for us are these two blocks, so the self-attention and the MLP, because they all have the more or less similar structure. So they're composed of the linear operator, like a sequence of instances of the torch and nonlinear, for example. And they're all doing just like the matrix-matrix multiplications during a forward pass in order to produce the token at the output. If we take this model now, and we do like a measurement, so we do profiling, to see where do we actually spend time during a forward pass. So this is example for Llama 8B model in the BF16, so like a full precision model, unquantized. This is how it would look like. Basically, like this huge, like a green bar here represents all of the linear operators inside the model. Everything else here, all other colors are like some other operations like layer norms, moving the data around and stuff. And because this is the like 80% of this bar, this is what we want to focus on during the quantization process. This is what we want now to optimize. So this graph would change a bit if we have like a really, really long context, because at that point, then attention becomes very, very expensive part. But for most of the use cases, this is going to be how the trade-offs are going to look like. If we now quantize this model, like for example, we go from 16 bits to 8 bits, and we run again the same profiling, and we take a look at the graph, we can literally cut the cost of this green piece here of all of the linear operators by half. This means that now we have a close to 2 times smaller model, which should be more or less 2 times faster in practice. So the main takeaway from this is that the part that all of the quantization is about is focused on quantizing all of the linear operators inside the model. All other layers like embeddings, the layer norms, LM head are usually kept in the full precision because their runtime cost is not as significant as the runtime cost of the linear layers. So how this looks in practice? So basically, inside our server, where we have the GPUs, at the bottom level, we have the CPU. So this is our main memory, which is really large, but it's also very, very slow. Then on top of that, we have our GPUs, which have this high bandwidth memory, or HBM. This is what we get when we run NVIDIA SMI, so that's the HBM memory. And this is much smaller, but also much faster memory. And then on top of the HBM, we have GPU SRAM and tensor cores. This is where the actual computation happens, where the actual matrix-matrix multiplications are happening. And this is the smallest part of this entire stack, but it's also the fastest to operate with. So when we want to do like inference pass, we take our model, we deploy it on a server, we try to run one forward pass to generate one token. What's happening is that we load the model first from the CPU memory onto the GPU memory, and this happens only once. So this is like a reasonable cost that we pay only once we start our deployment. And then what we do n times for all of these linear operators, which are like the most kind of expensive pieces of our inference stack, we load the linear layers from HBM. So this is where our model lives. We load it inside the SRAM and tensor cores. We split it in small chunks. We do the computations. So we do matrix-matrix multiplications. We store back the results, and then we move to the second layer. And then we repeat this n times for all linear linear operators in all layers in the model. Because we are repeating this n times, and n is like usually very large for the models that we are dealing with these days, these are the most like the two most interesting pieces that we want to optimize. And this is what we actually want to accelerate with quantization. So the first part is basically how do we accelerate loading of these like a linear operators, which are actually the weights of our model. The GPUs that we have and the servers that we have, they have like a fixed constraints, which they're built with. Like they have like a fixed bandwidth and the speed at which they can read the data. So we cannot do anything there, but we can reduce the amount of data that we need to load. So basically, we do this by reducing the number of bits which are used to represent the weights. So instead of reading and writing back 16 bits for each weight, we can reduce this to 8 or 4 bits and therefore get like 2 or 3x speedups. And the solution for this specific optimization is to do weight-only quantization. And this is, for example, what the entire OLLAMA and Llama CPP community is doing in order to enable you to run LLMs locally on your laptop. The second part is this computational part. So once we load the linear operators, we get some inputs from the user, and now we have to do a lot of matrix-matrix multiplications in order to produce a token at the output, which means that now we have to accelerate the computational part, which is happening inside the tensor cores. So basically, because this computation is happening inside tensor cores, the solution is to get faster tensor cores. If we look at the technical specification of H100 GPU, we see that, so this is where we are operating by default. All of the models are coming these days in BrainFloat 16, and the speed that we're getting these days from H100 are like close to 2,000 teraflops. And that's what we can get. And if we look at this technical specification, we see that this GPU also has two more tensor cores, FP8 and INT8 tensor cores, which have 2 times more teraflops. Which means that if we are able to leverage these lower precision tensor cores, we can get almost 2 times faster model, like 2 times faster matrix multiplications. In order to trigger usage of these lower precision tensor cores, we have to have both operands that are going inside the matrix multiplication to be in the specific data type. For FP8, they both have to be in the FP8 format. For INT8, both have to be in INT8. And this means that in this specific case, if we are optimizing for compute and we want to trigger these lower precision tensor cores, we have to quantize both operands, both weights and activations. The kind of just a side note here is that FP8 tensor cores are only relevant if our GPUs are Hopper, Ada Lovelace, and the newer GPUs like Blackwell. Whereas if we are dealing with the older ones like Ampere, then we have access only to INT8. This is going to be relevant later on when we have to decide which quantization scheme to use. Both offer the same speed up, so the same number of teraflops. The only difference is that the FP8 gives us much better accuracy recovery, and it's much easier to apply it in general in practice. So now that we have seen basically how to do, actually which quantization schemes exist, so weight-only quantization and weight and activation quantization, now we can take a look at how to actually quantize some LLMs in practice. For this purpose, our team has developed a library called LLM compressor. So this is a part of the vLLM project. And it basically gives you the opportunity to quantize all LLMs which are supported in Hugging Face transformers in this post-training regime. So we do not support quantization aware training, which is like the other way of doing the quantization during training by simulating the quantization process. This is like something called PTQ in practice, and this is something you can do relatively cheaply after you train your model. And in addition to quantization, it also supports pruning. So in case you want to do pruning, you can do that as well. And inside the LLM compressor, we have 2 different ways of using it. One is for practitioners, one is for researchers. And what I mean by this, so for practitioners, we have developed so if you just want to quantize your model, you don't want to deal with the hyperparameters of quantization. You don't want to tune different things. You just want to run the quantization and get a model with reasonable accuracy at the end that you can just deploy. This is the pathway that you should be using. So basically, our team developed a set of very optimized recipes for different quantization schemes, which you can just apply very easily with a simple Python script, and then get models which are pretty stable in terms of the accuracy recovery. The second pathway, so many quantization researchers usually want to experiment with many different things, or if this way for practitioners doesn't provide you with a really good model that you're satisfied with, you can then start tweaking more knobs for quantization specifically. And what I mean by this is that the LLM compressor has kind of this implementation of fine-grained control over quantization scales. So this basically means that this process that I talked at the beginning, so we are mapping the weights from BrainFloat 16, for example, range to much smaller range like INT8, and we need to find the proper scaling factor to downscale all of the weights. Usually, the simplest approach is to find one scale for the entire matrix. Unfortunately, this is not always very accurate, right? And we can take more granular approach here by finding one scale per channel, one scale per group of weights, and so on and so forth. So we can change this granularity in order to get the better scaling factors for groups of weights. Then we can also do symmetric, asymmetric quantization with or without calibration data, with activation ordering, dynamic, static, and so on and so forth. There's a lot of different pieces that you can tweak if you really want to do it. And the final part here is that all of the models produced by LLM compressor are saved in the compressed tensors format. So this is the format that our team developed, and it has been adopted also by Hugging Face and all other companies who are now like deploying the models in compressed models in vLLM. It's basically an extension of the safe tensors format. So it gives you all of the features that safe tensors have. And then on top of that also does the proper packing of the quantized weights, such that once you load them or like decide to deploy them in vLLM, they will trigger optimal inference kernels in vLLM. So it's like tightly packed with vLLM. If you're deploying models with vLLM, this should be the format that you should be using. So this is basically how simple it is just to like take this path for practitioners in order to like, for example, quantize your model to FP8 format. So it's basically you just load your model. So this is the standard Hugging Face transformers, auto model for causal LLM, dot from pre-trained, like the standard thing. And then on top of that, we just have the small piece which is like irrelevant for quantization. We specify that the targets that we want to quantize are all linear operators in our model, and the scheme that we want to apply in this case is FPA dynamic, where dynamic stands for the dynamic activation of dynamic quantization of activations. You'll see later on why this is relevant. And then we just call a one-shot method. We provide the model, we provide the recipe, and that's it. We save the model as any other Hugging Face transformers model, and it will be saved automatically in the compressed tensors format, so you can directly use it inside vLLM and get the best kernels in vLLM for inference. Going back to this dynamic piece here, as I mentioned before, so when we are doing quantization of weights and activations, and for activations specifically, there are two ways to quantize them. One is to do it in a static and a dynamic way. Doing dynamic activation quantization means that we are doing that on the fly. So during the runtime, while the inputs are coming inside our model, so the prompt is coming in, and we are passing it through the layers, we are estimating the range of the activations in order to quantize them, and we are quantizing them on the fly. This comes at the small, because we are running this during the actual inference, this comes with a small cost in the runtime. The other way to do it in a static, with the static activation quantization, means that we have to do it by using some calibration data. The calibration data is like some small set of words or tokens that we need to pass through our model during the quantization phase in order to estimate the range of the activations such that we can quantize them properly. This is very relevant for LLMs of the size that we are dealing with these days, because they have very large outliers. So if you're not familiar with that, outliers are like some specific channels. We still don't know why they happen, why this is the case, but it's like an artifact of the training process. They have like order of magnitude larger values than any other activation in that specific layer. And this means that during the quantization process, we actually need to trigger this behavior with the calibration data just to see what is the range for the outliers, so we can quantize them properly. So the second example here is going to do exactly that. In this specific case, the start is the same. We just load the model as any other model. And now we need, because we want to do the calibration data set, we load, like we have a predefined calibration data set on our Hugging Face hub. We just load it, tokenize it, just the standard Hugging Face stuff. And then we compose a recipe for quantization. Previously, it was just FP8. Here, I'm just showing how to do int8 in this case. And the only difference is that now for int8, we want to use like smooth quant modifier, which is basically a paper which showed that there is a way to make this quantization of activations easier by introducing some specific scaling factors to distribute the hardness of activation quantization on top of weights, which are usually much easier to quantize. So you just kind of compose different quantization algorithms here. You run the one-shot as before, but in this case, the only difference is that we also specify the calibration data set, and that's it. We save the pre-trained model. If you just want to do int4 weight-only quantization, it's very easy. We just drop the smooth quant modifier, which is relevant for activation quantization. We change the scheme to W4A16, and that's literally it. So very, very simple interface to use. In case you want to play a bit more, so this is now this other path for researchers, where you can actually specify a recipe in this form, where you get access to every single part of the quantization process, both for weights and activations. So you can specify all these different pieces for each layer specifically. So you can play with many different configurations. Okay, so now let's take a look at the accuracy. As I mentioned on the first slide, when we're doing quantization, we are introducing some quantization error because we are mapping weights which had different values in brain float or FP16 to buckets of the same values, or we are shifting them somewhere so that we can fit them in a proper bucket. And because we are changing the weights of the model, the most kind of reasonable question to ask is what happens with the accuracy because of that. What I'm going to show here is the study that we did in the paper called "Give Me BF16 or Give Me a Death: Accuracy Performance Trade-offs in LLM Quantization," where we basically took all of the benchmarks that exist out there. So you should not read all of these numbers. I just guide you through the relevant pieces of it, just kind of to show the scale of the evaluations that we did. So we basically took Llama 3.1, which was a perfect a model family because it had the smallest model, 8B up to 4 or 5B, so that we can demonstrate what happens with the accuracy recovery for very small and for very, very large models. And then we looked at the 3 quantization schemes, which are mostly used in vLLM, FP8 quantization of both weights and activations, int8 quantization of weights and activations, and int4 weight-only quantization. And then we tuned all these hyperparameters with LLM compressor, and then we ran more than a million evaluations in the end. And basically we did evaluations across MLU, Chain of Thought, ARC Challenge, GSM8K, HelaSwag, blah, 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 all these popular benchmarks. The main takeaway that we found was that once calibration is tuned properly and done in a proper way with the fine-grained scales, we can get the models which have usually in the 95 to 100% accuracy recovery range, which means that we get two or 3 times smaller model, and the price that we are paying in the accuracy is anywhere from 1 to 5% relative to the unquantized model. So the main message kind of to take, and you will see that across all other evaluations that we'll see, is that usually FP8 and int8 are close to lossless in the 97, 98 up to 100% recovery range, and int4 is usually a little bit harder to do, and the recovery range is 95 up to 100. But that's basically we haven't seen lower than 95 once it's calibrated properly. So yeah. Then this first part, this was the Hugging Face OpenLLM Leaderboard V1 collection of tasks. Then Hugging Face came with the new leaderboard called Leaderboard V2 because Leaderboard V1 got saturated with modern LLMs, which got really high scores. So then they introduced Leaderboard V2 with much harder evaluations like instruction following eval, Big Bench Hard, Math Level 5, GPQA, and so on and so forth. Then we took, again, the same approach, the same models, we evaluated them there, and then we got more or less the same story, above 95% accuracy recovery across all of the models, with smaller models and int4 dropping a little bit more than all other models, which are usually 97 to 100%. And then we also looked at the second set, real-world tasks, Arena Hard, Human Eval, Ruler is a Human Eval. Arena Hard is a chatbot arena style evaluation. In this case, this is the automated way of using, instead of using human judgments, it's using ChatGPT, some version of ChatGPT as a judge. Then Human Eval is the standard coding benchmark. Ruler is a collection of, I think, 12 different tasks which are testing the models on a long context. And then we are more or less seeing the same story across all of these. Then reasoning models became very popular recently, so then we did the same approach with reasoning models. We took DeepSeek R1 Distill family, which had all of these models, from Llama 8B, Llama 70B, Quen 1.5B up to Quen 32B, and we literally did the same approach as before, and we looked at FP8, int8, int4 across AIME, Math 500 and GPQA, which are like the standard reasoning benchmarks that everyone's using these days. And we got more or less the same story. FP8 int 8, like close to indistinguishable to to unquantized BF16, and int 4 usually drops a bit more for smaller models like here and here you can see for Llama 8b and Qwen 1.5b. This is a fresh result from last week. Basically, last week DeepSeek released a new version of the R1 model, which is this like 670 billion size model, which can do like reasoning close to the modern like these closed source models like O3, like Claude and so on. And basically we did the quantization to int 4 and got like a score of like average recovery score of 99.82%, like a model which is very, very close to like the unquantized baseline by just doing the standard LLM compressor quantization. In addition to LLMs, all of this, the entire story fits well with the visual language models. So this is just an example of the Pixtral large model. Again, the same quantization scheme, just a different set of evaluations, which are covering now the vision inputs in addition to the textual inputs, and the story is more or less the same, to avoid repeating myself. So the final part about the accuracy of quantized models. So they're like in the standard academic world, in the research papers about quantization, the standard setup is always to take a model, quantize it down to 8 bits, 4 bits, or any other like a scheme, and then compare accuracy recovery relative to the unquantized model. And then we see how well we perform. And this is a perfect benchmark in the academic setup where we want to compare different algorithms to see which one is the better at quantization. However, in the real world, when we are deploying models in practice, the main question that we are kind of faced with is what is the best accuracy that I can fit on a specific GPU that I have. Right, that's the main constraint we care about. And quantization. So without quantization, what we would usually do, we would take a look with, let's say, we are allowed to spend 14 gigabytes of the GPU memory for our deployment for some use case. Without quantization, the only thing we can do is take a look at all of the available models and see which model fits inside of that GPU, and that's it. In this case, for 14 gigabytes, the best model, for example, we can fit is Qwen 7b at BF16. It has a average reasoning score of 65.8, for example. And that's the best thing we can do. There's nothing else we can play with here. However, quantization unlocks this additional path to improve the accuracy of our deployment by going up in the model size, so taking a much larger model, which doesn't fit originally on our GPU, and then during the quantization process, reducing the number of bits to fit it inside the desired GPU. In this specific case, like this Qwen 7b, 14b lends itself perfectly for this example. So we go up to Qwen 14b, which is 2 times larger and therefore doesn't fit on our desired GPU. But then we quantize it down to FP8, int 8, or int 4, like any specific quantization scheme we're interested in. And in all of these cases, even if we lose some of the accuracy, from 1 to 5%, let's say, we are still way better than the smaller model in the unquantized form. So just by going to the Qwen 14b, quantizing it down to like the range that we can fit on a GPU, we improve our reasoning score from 65 to the range of 72, 74. And that's basically this additional path that quantization unlocks for us, just kind of to deploy better models in practice. So larger quantized, is always better than a smaller unquantized. So we are now satisfied with the accuracy of the model. We quantized the model. We got the desired accuracy that we are satisfied with. We want to deploy it. But now the next question is, what are the speedups that we get from our quantized models? Quantized models do not provide always the speedups relative to the unquantized models, and that's the part that we have to be careful about, and that's the reason why we have to do profiling, as one of the previous speakers also pointed out. So here we are looking at the inter-token latency, how inter-token latency changes with the number of queries per second for Llama 8B model served on a A6000 GPU for some specific docstring generation use case that we came up with. And we are looking at 3 different models. BF16, that's the blue line here, like unquantized model, int8 weight and activation quantized model, represented by the yellow graph here, and int4 weight only quantized model, represented by the green graph. So basically, there are 3 interesting points to observe on this graph here. So first, if we are in the range of like less than 4 queries per second, so our server is not that busy, we have just a few users, the best model that we could deploy in terms of the latency is the int4 weight-only quantized model, right? It gives us the best latency. However, once we hit 4 queries per second, what happens? Like there is this kind of shift, and int8 weight and activation quantized model becomes a better choice for us. Why this is happening? Because when we are in the range of, let's say, in this specific use case, less than 4 queries per second, our GPUs are not busy by doing matrix multiplications. They're mostly busy with moving the data around. And what this means is that we are like the time we spent doing the operations inside tensor cores is not comparable to the time that we spent just to load the weights and move them back. And this is the reason why weight-only quantization is a better choice. And this is usually called like a memory bandwidth regime. So the only like a bottleneck that we have is the memory bandwidth. So how quickly can we read the weights and write the results back? Once we cross 4 queries per second, for this specific model, on this specific GPU, what happens, it happens that we are switching over to a second regime. So this is a compute-bound regime, because now we have large enough inputs, so we have a lot of users coming in. So many users that our tensor cores are going to be busy doing actual matrix multiplication. So now in this case, the time that we spend on doing matrix multiplication is much more significant than the time needed to load the weights and write them back down. So this is now the compute-bound regime, and that's the reason why now we benefit more by doing weight and activation quantization, because in this case we can leverage these lower precision tensor cores, which have 2 times more flops than the original unquantized ones. And the last interesting point in this graph is that once we cross, for example, 5 queries per second, unquantized model becomes better choice than the int4 weight-only quantized model. This is because we are now heavily bounded by compute, and basically the cost to load the weights is negligible relative to the cost of doing the actual computation inside tensor cores, which means that the int4 weight-only quantization, or any form of the weight-only quantization, will just bring us additional overhead from unpacking and packing the weights. Because what happens with the weight-only quantized models is that they only give us speedups when we are in the like a latency-constrained regime, so when we don't have a lot of users, and our main cost is just reading and writing back the weights. So yeah, the main point here is that you have to be careful when you're deploying the models. You should always do some form of like a benchmarking, like trying to simulate the actual workloads that you see in your deployment to see actually how these trade-offs look like in practice. And for this specifically, we built a tool called Guide LLM, which is also like open source, and it's going to basically enable you to automate this entire process. You just like deploy your model with any inference engine. In this case, you can do vLLM, AgileLang, whatever you're deploying the model with. And then its Guide LLM will simulate the actual, like a real workloads that you specify, and it's going to produce like something like a fancy report like this. So you can basically take a look and see which quantization format is best for your specific deployment. And yeah, some useful links at the end, at least for my part. LLM compressor, Guide LLM. If you don't want to quantize the models on your own, you just want to leverage the existing ones, you can go to the Red Hat AI's Hugging Face Hub. So that's basically where our team is like, I mean, I think right now we have around 400 models. And we are actively releasing, whenever there is a new model, we do all of these quantizations for you, and then we release them publicly, so you can just download them from our Hugging Face Hub and just use them on their own. One example was, for example, DeepSeek. So basically, in a matter of 1 or 2 days, they will, like, once they are released, they will be on our Hugging Face Hub, and then link for vLLM. a nice thing, kind of a nice like acknowledgement for all of the work we're doing with LLM compressor as part of the vLLM project has been the recent Llama 4 models from Meta, where Meta actually collaborated with us and they adopted LLM compressor for their own like FP8 quantization of the Llama 4 model, which was a huge kind of acknowledgement for all of the work we did there. Yeah, so now Max is going to take over.
Yes. So I want to almost close, but I start with a few questions. First of all, who of you have already deployed their own LLM on their laptop, on a GPU, in the cloud, wherever? Okay, that's a lot. Who has deployed quantized models? 50%, 60% maybe? So all the other 50%, I hope you got the message. And that's what I would just briefly conclude from a real world project where we actually did that. So we had users leveraging a Mistral 7B, so small model. And the question is, they complained about hallucination of the model and that it doesn't fit to their quality needs and so on and so forth. And we had to ask us these questions because the GPUs that were there were just L40S. They have 48 gig of RAM. So we had to make some considerations, which models could we use? And we were in the same spot like the 50% of you that haven't deployed quantized models back in the day. And yeah, so we were asking us these questions, how can we best utilize the hardware? What are the power and the pitfalls of quantization? We learned a lot about that today. It's really depending on the approach and the workload profile. And then lastly, can we actually we gain more quality by employing a bigger model, but what is the performance trade-off? Those were the questions we were asking ourselves. And of course, what we needed were, of course, an inferencing stack. And we as Red Hat, we provide something which looks somewhat similar to what we have seen in the morning when Roger presented. Of course, an enterprise stack, but we build it on Kubernetes and OpenShift here with the Open Data Hub. And we have as well vLLM. And here we leverage the models from Hugging Face to actually test the approach. And we wanted, we of course leveraged Guide LLM because it's really nice if you want to have upfront view into how many concurrent requests can my model serve. When is my GPU at the limit? What's the sweet spot where it spits out the most tokens? That's what Guide LLM is doing greatly for you. And well, first of all, before I talk about the test results, when we compared the unquantized Mistral Small 24B with quantized Mistral Small 24B versus Mistral 7B. So unquantized, unquantized, quantized. What is very important to look at is the memory consumption, just at the first step to think about, does it actually fit into my GPUs? And I said we had L40S GPUs here available. They have 48 gig of RAM. This model, it didn't fit, so we couldn't test it because it consumed, just the weights consumed 44. Then we always have some overhead from CUDA and from PyTorch if we're leveraging NVIDIA here. So we couldn't actually test it because we immediately ran into out of memory. The quantized model here, we could test, and we look into the quality, you can already guess that it's again just 1 or 2% less than this model, so it's not a big deal. Cool thing is, we almost have 50% of the GPU left, which is very important for something called the KV cache. It's the key value cache, which is a determinant of how fast your model can respond to you once it's in production and used by many users. And obviously, even more memory was available when we had the smallest model, just 7 billion parameters, Mistral 7B. So now let's look at quality versus performance. And again, I don't want to put you again through all of the benchmarks that Eldar has already put up. In a nutshell, as I already indicated, from a quality point of view, we didn't do the benchmark. We just took them from the leaderboards from Hugging Face. And we can see already that it's a very good deal to take this model here, the quantized version, FP8 dynamic quantized version of Mistral Small 24B. Compared to Mistral 7B. So the hallucination problems we can hopefully solve with that model. That was the assumption. But what about the performance? So how slow does it actually get? And again, here it's just like we've seen from Eldar with the inter-token latency. we have to distinguish. If we have just a few users, we can see here with synchronous, with the test strategy called synchronous. So in synchronous way, we shoot several requests at the model. It spits out 74 tokens per second. This is the small model. And the bigger quantized model spits out just half as many tokens. That's 50% less. So we get 2.5 the quality, or so if we go to the previous page, or do I do it that way? Right, so we have 19 here, we have 51 here, approximately 2.5 in terms of quality, but we lose 50% of the speed. Of course, probably still okay if my model is doing kind of, let's say, bullshit. I rather wait twice as long and have good results. But still, well, maybe I'm not, with bigger models, I may don't take the trade-off. But what is important, as soon as I put it under substantial load, I can see that the gap is actually melting away. So it can, owing to what Eldar just explained, and the parallelism of matrix multiplications, it can spit out much more tokens per second. So the small model, almost 1,400 per second. The Mistral small 24B can spit out 1,100. So we just get about 20% decrease in latency. So the key message here is for anyone that is employing their own large language models, you should look into quantization. All right, thank you very much. Any questions?
Thank you very much for this very nice explanation of quantization. So the question is, what I got, like you should make sure that you deploy quantized models to speed up the inference, right? And there are like also quantization aware training of the models, like where you kind of like during fine tuning or during training, you emulate what inference would happen during quantization. So let's say if we are fine tuning a model, and we know that this model goes into production, like should we make sure that we do quantization aware training? And like the scores that you showed for recovery, was there any the simulation quantization done on this evaluation, or is this like pure recovery rate just like during inference?
Yeah. So basically, the main trade-off between this, so all of the results I showed here are obtained with post-training quantization. So just like fine-tuning your model in any way that you want to fine-tune, and then just doing one-shot quantization. The main reason for this, and that's what we also implement in the LLM compressor, is the fact that you don't need the entire infrastructure to run quantization, right? For quantization-aware training, the main trade-off is that you have to train the model. And then there is a lot of things like, if you want to train a very large model, like you have to have GPUs, you have to have the training library, you have to have the proper data set, you have to configure all hyperparameters, like all of these pieces that go into descendant training. Quantization-aware training is usually always more accurate than post-training quantization. So there is a chance that you can reduce this gap. Now it's just a matter of whether it makes sense for you to do it, because with properly tuned post-training quantization, you get to the range 95, 96, 98, sometimes 100% accuracy recovery. And now it's like the matter of like, do you actually want to invest all of this time to get 1 or 2% more on the accuracy recovery side? But usually you should always get better results with quantization-aware training versus the post-training quantization. But yeah, the compute cost and everything else associated with that is much, much larger.
Okay, now it works. Okay, so I have one more question. So you probably know about 1-bit models, which is, in my understanding, is the extreme case of quantization, right? And you showed that very large quantized models, they perform better than like small non-quantized. So where's this trade-off? Because like, should we take a massive model, do it like all 1-bit, like, or like, where would you see like the trade-off between like the degree of quantization and the size of the model?
One very, very unfortunate thing with 1-bit and all these like very extreme cases is the fact that usually they do drop a bit more on the accuracy side than what most users are comfortable with. So usually these days you'll find 1-bit, 2-bit models and so on, but they don't have, if you look at the model cards, most of them don't have extensive evaluations. And that's one of the reasons we do have some data on that. We did investigation. And usually what we say is that if you really want to have like accuracy recovery, like 95% and more, like we don't yet have methods to do it at lower than 4 bits. If you're comfortable by dropping 5 points, 10 points on some benchmarks, then you can definitely go below 4 bits. But then it's just a matter of the trade-off, like whether you can accept that or not. Yeah. And also, like the larger models, very, very large models, are still going to have a lot of the cost just because they have a lot of layers. Like doing 1-bit DeepSeek R1 would still be, even though it's 1 bit, it's still going to be expensive because you have a ton of layers that you're going to still have to load and like move the data around. Yeah. So yeah, this without proper benchmarking, like for example with GuideLM, like looking at the trade-offs, it would be really, really hard to say, oh, this is a better choice than this one. It's very specific to GPU type, amount of the memory that you have, and the model.
Thank you very much.
Thank you.
Thank you.